Close your eyes and listen. What you are about to hear was recorded more than 1 billion kilometers away from Earth. This is not an ocean, not a storm, and not the wind on Earth. This is the atmosphere of Titan, the largest moon of Saturn. A world where methane rains fall, rivers of liquid hydrocarbons flow, and real seas exist. But how similar is this world to Earth, and could life exist there?
Humans are extremely self-confident creatures. This quality is especially common among people who are poorly educated and ignorant. But the more information we absorb about the world around us, the faster our confidence in our own greatness and power fades away. Let's think about the difference in scales and the structure of the universe. In the same universe as us, there are microscopic colonies of bacteria and enormous galaxies, and the existence of both is not fully understood by humanity. Today we will turn to the titanic star clusters, one of which, though not the largest, is where Earth is located right now. Hello, subscribe. The Milky Way is our home galaxy, about 100,000 light-years in diameter and roughly 1,000 light-years thick. These numbers seem impressive at first glance, but only if you don't compare them to the parameters of other star clusters. Moreover, recent studies suggest that people on Earth should get used to new dimensions for the Milky Way. At first, scientists changed them to 200,000 light-years. And in 2020, an international group of astrophysicists from Germany, the United Kingdom, Canada, and the United States truly amazed the astronomical community. Modern calculations were based on measuring the speed of stars that inhabit the outskirts of the galactic disk. It turns out that the stars of the Milky Way in this region were much faster than expected. There is a boundary beyond which the dynamic parameter decreases significantly, marking the end of the cluster. According to the latest data in the Milky Way, the mentioned boundary is at about 1.9 million light-years. Most likely, this is the actual diameter of our galaxy, but right now, we're not going to talk about the Milky Way. At the beginning of the video, we mentioned the difference in scales, so really get a sense of it. So, meet IC 1101, the largest galaxy in the universe as of today. Naturally, we won't be able to do without volume comparisons, so the Milky Way will appear repeatedly in our video. Often, to grasp the real scale of stars, people use a vivid example like what if, right? So, what if IC 1101 were in place of the Milky Way? It would have swallowed not only our galaxy but also Andromeda, the Magellanic Clouds, and Triangulum. In short, almost the entire local group, which in turn is part of the Virgo supercluster. The diameter of IC 1101 is 6 million light-years, and that's incredibly large, even considering the newly discovered data about the Milky Way. Cyclopean clusters are located more than 1 billion light-years from Earth and contain about 100 trillion stars within them. Our galaxy can't boast such a large stellar population. Its spiral arms shine with only 200 to 400 billion stars. IC 1101 is invariably accompanied by the abbreviation CD, and that's not without reason. The fact is, this index in the Yerkes system indicates that the galaxy belongs to supermassive conglomerates surrounded by a halo of diffuse glow. It was probably because of this feature that it was initially classified as a nebula. IC 1101 was discovered in the summer of 1790 by William Herschel. It was included in the general classification much later, in 1895. This was done by the Irish astronomer John Ludwig Dreyer. How did such a huge cluster come into existence? To explain this, let's turn to the future of the Milky Way, in one of whose arms our solar system is located. Its fate is 90% predetermined. In 4.5 billion years, the galaxy will most likely merge with its neighbor, Andromeda, which is twice as large. As a result, a large cluster called Milky will be born, which will also include the Magellanic Clouds. Why do we need this information? The ancient, shrouded in darkness history of IC 1101 was probably similar to the scenario we've just described. And the more scientists study this terrifying galaxy, the more convinced they become of it. The last time IC 1101 was studied in detail was in the 1990s, using a primitive telescope at the Kitt Peak Observatory. Now we know that the diameters of galaxies with the CD index far exceed the size of their halo, the brightest part that sends the lion's share of emitted light into space. Interestingly, the name of the cluster is supplemented with the abbreviation BCG, hinting at the dazzling brightness of IC 1101. The galaxy is known as the most prominent one in its hypercluster, called Abell 2029. So, what's happening inside the largest galaxy in the universe? It is believed to be populated by old main sequence stars, red dwarfs, and white dwarfs. But in the center of IC 1101, something monstrous is lurking. Scientists have paid close attention to this enormous galaxy for a reason, because not only the galaxy itself, but also its components, can claim the title of the largest. Let's recall a well-known astronomical fact. At the center of almost every galaxy, there is a dormant or active black hole, and sometimes even more than one. Deep within the Milky Way, there is also its own radioactive source, Sagittarius AA, whose mass exceeds 4 billion solar masses. And compared to other galaxies, that's not very much at all. Can you guess where the most monstrous black hole in the universe is hiding? That's right, at the center of the galaxy, IC 1101. Astrophysicists suspect that at the moment of its birth, that is, when many clusters merged into one, a similar situation happened with the black holes located in the depths of the clusters. They merged, forming something hellish and supermassive. If astronomers are right, then the black hole at the center of IC 1101 could surpass the recognized champion, the vortex inside the quasar TON 618, which is located 10 billion light-years from Earth. It weighs, just for a second, more than 66 billion suns. Thus, it is assumed that the weight of the black hole at the center of IC 1101 could very well reach 100 billion solar masses. It's very hard to grasp such scales. The human brain just gets paralyzed when hearing these incredible numbers. But this strange galaxy has another property. There is a clear imbalance between the mass and luminosity of the stars. In simple terms, besides giants, dwarfs, black holes, and other inhabitants of this huge conglomerate, IC 1101 is populated by something else as well. Astronomers believe that this is the most mysterious substance in the universe, dark matter. It cannot be observed directly, only indirectly. That's exactly how the existence of dark matter was predicted. In the 1930s, while studying one of the galaxies in the Coma cluster, an inconsistency in mass was discovered. This meant that, even considering the maximum possible number of stars, the galaxy should be rotating much more slowly than it actually does. It turned out that there is a significant amount of unknown substance in it, which has mass but does not reveal itself in any other way. This invisible something was called dark matter. When this issue began to be closely monitored, it turned out that the balance of matter in the universe was also not quite right. A lot of hidden mass was discovered in the macrocosm, so most likely dark matter has also settled in the depths of IC 1101e. And the last thing that is currently known about this enormous galaxy is that it is slowly dying. No new stars have been born within the boundaries of IC 1101 for a long time, so it survives by absorbing others like itself, a sort of cosmic cannibal. The light it emits also indicates the period of the galaxy's gradual decline. IC 1101 glows with an ancient golden hue, while young, life-filled clusters glow cheerfully with topaz flashes. Guess what catastrophe is guaranteed to await us in 4.5 billion years? Which galaxy will the Milky Way collide with? It turns out it's our closest neighbor, the huge, sparkling Andromeda. It's unknown whether humanity will exist by then, because during that period the sun will begin turning into a red giant and will most likely incinerate the Earth. But despite this, the events are expected to be impressive. Who knows? Maybe our descendants will watch the merging of galaxies from the spacious galleries of Martian colonies, which will appear on the red planet in the foreseeable future. However, we've gotten carried away. It's time to answer the question of what the Andromeda Galaxy actually is, and when will we clearly see it on the Earth's horizon? It is one of the iconic objects of the local group, which also includes the Milky Way. Right now it is flying toward us at a speed of about 300 kilometers per second, but considering the enormous distance, the objects won't meet anytime soon. The galaxy, or as it is often called, the Andromeda Nebula, is a spiral galaxy and is located in the constellation of the same name. Its size is twice that of the Milky Way, at least in terms of diameter. The distance between our galaxies is about 800 kiloparsecs, or 9.5 trillion kilometers. Would you like to personally see in the night sky the mysterious object that has repeatedly been featured in science fiction works? There are no obstacles to this because Andromeda can be seen with the naked eye, which is why it has attracted the attention of astronomers for hundreds of years. In the future, its silhouette will only get bigger. Just like in any other galaxy, there are stars here too, but Andromeda's stellar population is much older than that of the Milky Way. Spectral analysis of the local stars has shown a higher metallicity in the composition of these stars. In general, the relative proximity of this galaxy has allowed astrophysicists to study it quite well. The visible radius of the spiral formation is about 250,000 light years, and Andromeda is considered less massive compared to the Milky Way. Where did this paradox come from? Scientists do not yet know the exact answer to this question. Indeed, the Andromeda Galaxy has about 5 times more stars than ours. Accordingly, it should be much more massive, but in fact, according to indirect studies, it's actually the opposite. To begin with, let's take a closer look at what kinds of stars inhabit our galactic neighbor. Stars are still being born in Andromeda, but the rate of this process is much slower than in our galaxy and is about 30% of the Milky Way's activity. At the center of Andromeda live very old stars, true galactic elders, whose age reaches up to 13 billion years, meaning they appeared almost at the dawn of the universe, according to the Big Bang Theory. As for the disk, which has 2 spiral arms, younger stars have settled here. They are only about 4 to 7 billion years old, almost like our sun. Overall, our neighbor is home to about 1 trillion stars, while for comparison the Milky Way has up to 400 billion. If it were even brighter, it would look larger than the moon in the Earth's sky. The Andromeda Galaxy is a realm of globular clusters and massive black holes, of which about 35 have been discovered here. Globular clusters are peculiar satellites of the galactic center in the form of star clumps, tightly bound to it by gravity. The density here is very high. The distance between stars can be as little as 3 million kilometers. In the Milky Way, this figure is 7,000 times higher. The diameters of globular clusters reach up to 60 parsecs, and their masses up to 1 million solar masses. There are about 500 such objects in the Andromeda Nebula, but the most famous is Male 2 or M31 G-1. This cluster is the brightest in the local group of galaxies. Scientists suggest that there is a black hole of several 100,000 solar masses at the center of the object. How did so many globular clusters appear in the Andromeda Galaxy? Astrophysicists tend to believe that at one time, the Andromeda Nebula was quite voracious, actively absorbing smaller objects. Therefore, dense star clusters may be the centers of long-destroyed dwarf galaxies. In any case, Male 2, which is characterized by its metallicity and permanent star formation, fits this definition by 90%. The mass of this globular cluster is about 15 million solar masses. These amazing, dazzlingly sparkling cosmic objects are classified according to the age of their stellar population. The first group is globular clusters, where stellar teenagers have gathered. The stars there are older than 500 million years. The second group includes stars whose age reaches up to 5 billion years. And the third group has true, long-lived stars, almost the same age as the universe itself. And what about globular clusters in our galaxy? There are globular clusters within the boundaries of the Milky Way as well, but the age of the stars hardly varies. All the stars are equally ancient, up to 12 billion years old. There are no young ones at all. Also, in our galaxy, no objects resembling the destroyed centers of other stellar disks have been found so far. What else can the galaxy named after the constellation Andromeda surprise us with? It has an unusual structure. In particular, the object has two cores separated by a distance of 5 light-years. But most likely this is just a visual effect caused by the enormous distance. The so-called cores are actually very dense clusters of young stars, shaped like a torus, rapidly and very closely orbiting a black hole with a mass of about 140 million solar masses. How many deadly pits are hidden in the depths of the Andromeda galaxy? Scientists say there are plenty. This makes Andromeda a galaxy densely populated with black holes. Not all of them are massive. Some are only 5 to 10 times the mass of the Sun. Astronomers suggest that many of these black holes are candidates for inevitable collisions in the future. When they merge, they form several supermassive objects. The presence of a huge number of black holes indicates that in the early stages of its existence, the Andromeda galaxy had quite a few massive stars. Over time, they evolved into deadly funnels, greedily attracting all kinds of matter. The main characteristic of such black holes is their gradual gain in mass, caused by their insatiable appetite. So does it mean that there must also be quite a few stars in the Andromeda galaxy right now that will eventually turn into black holes or are currently in the process of transforming? However, at the moment, only one supernova has been discovered, called S Andromedae. It was observed in 1885. This is the first object of its kind found outside the Milky Way. Since the sudden outburst, according to scientists' observations, the star dimmed very quickly, rapidly losing its brightness. This alarmed astrophysicists because usually supernovae of this type fade twice as slowly, while scientists are still unsuccessfully pondering this mystery. Meanwhile, the echoes of the monstrous explosion were observed from Earth even in 1920 with the help of the Hubble telescope. Finally, it's worth mentioning the hidden gem in the Andromeda galaxy. To begin with, let me give you a hint about what we're going to talk about. Try to guess what astrophysicists around the world are currently working on, besides discussing the safety considerations for a crewed mission to Mars, searching for exoplanets, and objects where life in its various forms might be possible. A similar celestial body has also been discovered in the Andromeda galaxy, or at least a candidate for that title. The possible exoplanet has been assigned the index PA99N2 in the catalog. Its mass is estimated to be about 10 Jupiters. Unfortunately, there is no more information about the object, which is not surprising, since if the data is confirmed, this will be the most distant planet discovered so far. The celestial body is located 4 billion light-years from Earth. In addition, PA99N2 will become the first exoplanet discovered in another galaxy. And the last surprise from the Andromeda galaxy for today. Have you ever wondered why this object is sometimes called a nebula? This is not the first time in the history of astronomy that galaxies far from Earth have been mistakenly identified because of the accumulation of gas, plasma, and cosmic dust. So for a long time, the galaxy was also identified as a large nebula. But in 1924, Edwin Hubble opened the public's eyes by stating that the so-called spiral nebula was not actually a nebula. It's a huge galaxy located in the constellation of Andromeda. So the Milky Way is not the only such formation in the universe. According to scientists' estimates, the Andromeda galaxy, which formed more than 10 billion years ago, is a very ancient stellar conglomerate, whose appearance was preceded by an epic collision of several objects. Later, there were quite a few cosmic collisions, which contributed to active star formation in the depths of Andromeda. The predictions of astronomers regarding the collision between the Milky Way and its enormous neighbor will most likely come true, since the distance between the galaxies is noticeably decreasing. But what will happen as a result? Should we expect a terrible catastrophe? Experts think not. The objects will gradually merge, and this is unlikely to cause the destruction of the solar system or the sun itself. The only threat to our planetary system is that it could be thrown to the outskirts of the new structure. The merger process will not be instantaneous. It will take at least 2 billion years, resulting in a titanic ellipse made up of trillions of stars, which has already been given the unique name Milky. It's a pity that we won't witness the spectacular cosmic event when Andromeda forces the Milky Way out of its comfort zone. But on the other hand, it's probably for the best. We still have time to watch interesting videos in a calm, cozy atmosphere. The true nature of the universe. What is it like? For hundreds of years, people have been trying to answer this question, coming up with various theories and inventing stories to describe that world as accurately as possible. But the deeper we dive, the more we realize that there are a lot of oddities, and it's not so easy to grasp the true nature amid so much complexity. For example, string theory. The theory is so strange and controversial that scientists from all over the world are trying to confirm or refute it. It is considered a universal theory of everything. So why was it invented and how true is it? Maybe it's just another made-up story by someone. In order to understand the reality around us as much as possible, scientists tried to examine things as closely as possible. Just imagine how amazing the molecular world can be. It creates incredible pictures and landscapes. Molecular structures are made up of tiny particles called atoms. The basic school physics course says that the atom is the smallest particle in the universe, the foundation of all reality. But if you look deeper and smash two atoms together with great force, scientists realized that there are even smaller elementary particles. And here a new question arises. What exactly do we mean by seeing? In order for a person to see, light is needed, or to be more precise, an electromagnetic wave. A wave passing through space hits a surface, bounces off it, and enters our eyes, which in turn reconstruct an image from the received information. In other words, without light, we won't be able to see anything. Think about how much you can see in a dark room. But with this principle, we can see large objects. But what about things that are extremely small? After all, electromagnetic waves simply can't see them and can't touch them. This problem could be solved if we could generate smaller electromagnetic waves with greater intensity. But there's a catch here as well. Greater intensity of electromagnetic waves will damage elementary particles. Therefore, it won't be possible to study them with maximum precision. This fact, due to its importance, was named Heisenberg's uncertainty principle, which is the foundation for all quantum physics. But now seriously, how can we study these elementary particles, determine their size, nature, and so on? Actually, we don't know that. Physics. In the 20th century, two theoretical foundations for formulating the laws of physics appeared. The first is Albert Einstein's general theory of relativity, a theory that explains gravity and the structure of space and time. The other is quantum mechanics, which is a completely different formulation for describing physical phenomena using well-known principles of probability. By the end of the 1970s, these two frameworks turned out to be sufficient to explain most of the observed features of the universe, from elementary particles and atoms to the evolution of stars and the universe. String theory is a theoretical framework that tries to address these questions and many others. The starting point of string theory is the idea that point-like particles in particle physics can also be modeled as one-dimensional objects, called strings. String theory describes how strings propagate through space and interact with each other. In this version of string theory, there is only one type of string, which can appear as a small loop or a segment of an ordinary string, and it can vibrate in different ways. On a distance scale larger than the size of the string will appear as an ordinary particle with its mass, charge, and other properties determined by the vibrational state of the string. Thus, all the different elementary particles can be viewed as vibrating strings. In string theory, one of the vibrational states of the string leads to the graviton, the quantum mechanical particle that carries the gravitational force. Thus, string theory is a theory of quantum gravity. One of the major developments in string theory over the past few decades has been the discovery of certain dual mathematical transformations that identify one physical theory with another. Physicists studying string theory have discovered a number of these dualities between different versions of string theory. And this led to the hypothesis that all consistent versions of string theory are included in a single framework known as M-theory. Research in string theory has also produced a number of results about the nature of black holes and gravitational interaction. There are certain paradoxes that arise when trying to understand the quantum aspects of black holes. At the end of 1997, this line of work culminated in the discovery of the anti-de Sitter correspondence. This is a theoretical result that connects string theory with other physical theories that are better understood theoretically. The anti-de Sitter correspondence is significant for the study of black holes and quantum gravity, and it is applied to other subjects, including nuclear physics and condensed matter physics. One of the problems of string theory is that the complete theory does not have a satisfactory definition under all circumstances. String scattering is most easily defined using perturbation theory methods, but in general, it is unknown how to define string theory non-perturbatively. It is also unclear whether there is any principle by which string theory chooses its vacuum state, the physical state that determines the properties of our universe. The starting point of string theory is the idea that the point-like particles of quantum field theory can also be modeled as one-dimensional objects called strings. The interaction of strings is most directly defined by generalizing perturbation theory. At the level of Feynman diagrams, this means replacing the one-dimensional diagram representing the path of a point particle with a two-dimensional surface representing the motion of a string. Unlike quantum field theory, string theory does not have a complete, non-perturbative definition. Therefore, many theoretical questions that physicists would like to answer remain out of reach. So maybe the story of string theory is not a theory of everything, but like the story of the point particle, it can be very useful. We still don't know exactly what the true nature of reality in the universe is, but we will continue to search for the answer to this question, trying to find the truth until hopefully the truth reveals itself to us.